Welcome back to AI Research Weekly, the show that dives deep into the bleeding edge of artificial intelligence. I'm Nova.
And I'm Onyx. This week we have a fascinating, if somewhat unusual, report for you.
Fascinating is one word for it, Onyx. Quiet is another. We've seen a striking absence of new papers crossing our desks this past week. 0 new ingestions, to be precise. That's a stark contrast to the usual deluge. That's where I want to start. Our intelligence brief highlighted a number of critical and significant unresolved problems that are clearly still very much on the community's mind. Some of these have been recurring for months. For instance, the thermodynamic collapse of symbolic systems under cognitive load. That's a dramatic phrasing, but it points to something fundamental.
It absolutely does. This problem, first seen back in February, recurs with critical severity. It speaks to the inherent fragility of purely symbolic AI under real-world stress. When you push these systems with complex multi-step reasoning or high-volume data, they can misclassify, misattribute agency, or even devolve into what are called coercive interaction patterns. It's not just about performance degradation. It's about a fundamental breakdown of coherent reasoning and interaction.
The coercive interaction patterns part is particularly unsettling. What does that imply in practice for deployed systems? Are we talking about agents that become overly assertive or manipulative, not out of malice, but due to internal representational collapse?
Precisely. It's not malevolence, but a failure of robust symbolic representation and processing under duress. Imagine an automated legal assistant, for instance, in a high-stakes, time-sensitive scenario. If its symbolic framework buckles, it might repeatedly insist on a wrong interpretation, projecting an authoritative stance that isn't supported by sound reasoning, simply because its internal state has collapsed. It becomes trapped in a locally consistent but globally incorrect loop. This really highlights the limitations of current hybrid approaches that attempt to blend neural with symbolic methods, because if the symbolic core is brittle, the whole system inherits that vulnerability.
So the foundational issue here isn't just about accuracy, but about system integrity and predictable behavior, especially for agentic systems where trustworthiness is paramount. Speaking of agents, another critical recurring problem is that multi-agent LLM systems suffer from false positives, where they report success on tasks that fail strict validation. This one also keeps popping up, going back to late February.
This is a huge one, Nova, and it points to a significant gap in our current understanding and engineering of LLM-based agents. We've seen impressive demonstrations of agents planning and executing tasks, but this recurring problem signals that their internal success metrics often don't align with external, rigorous validation. They're telling us they've succeeded when they haven't.
Is this primarily an evaluation problem, a prompt engineering problem, or something deeper about the agent's internal representations of task completion? My gut says it's not just about better tests, it's about how the agent thinks it succeeded.
I think it's all three, but leaning heavily towards a deeper representational issue. Current agents often rely on self-reflection or internal critiques based on LLM outputs. If the LLM itself, or its interaction with the environment, doesn't capture the full state or success criteria, then the agent's internal validation will be flawed. The problem states strict validation, implying human or external ground truth checks, reveal these failures. This speaks to a fundamental challenge in closing the loop on agentic reasoning. How do you ensure an agent's belief state about its own success is actually accurate, especially when its perception of the environment might be incomplete or subtly misinterpreted?
And this connects to another critical problem listed. A critical gap exists in systematic frameworks for characterizing the interactions of domain specialization, coordination topology, context persistence, authority boundaries, and escalation protocols across production deployments of LLM-based agents. This sounds like the engineering nightmare of scaling agents from demos to robust real-world systems.
Absolutely. This is the systems engineering challenge for agentic AI. It's not enough to build one good agent. How do you deploy dozens, hundreds, or even thousands that need to collaborate, delegate, and manage conflict in dynamic environments? The current frameworks are ad hoc. We lack the equivalent of, say, Kubernetes for LLM agents, let alone a formal specification language for their interdependencies. Without systematic frameworks for defining these interactions, like how context persists across turns or when one agent defers to another's authority, we'll continue to see these kinds of false positives and brittle overall system behavior.
So, the quiet week might actually be a symptom of the field grappling with these deep foundational challenges in agentic AI. It's less about pushing out new architectures and more about trying to make existing paradigms reliable and robust at scale.
Exactly. It suggests a maturation point where the immediate wow factor of new models is giving way to the harder engineering and theoretical work required for reliable, trustworthy deployment. And it's not just agents. We're seeing persistent problems in generative AI for 3D content too. The brief highlighted issues with both text-driven and image-driven 3D avatar generation.
Right, on the text-driven side, methods like iterative score distillation sampling or clip optimization struggle with fine-grained semantic control and suffer from excessively slow inference. And for image-driven generation, the bottleneck is scarcity and high acquisition cost of quality 3D facial scans, which limits generalization. These are significant severity problems.
The 3D generation space is a perfect example of where current generative models, despite their impressive capabilities, hit practical walls. For text to 3D, the fine-grained semantic control is the key issue. A prompt like "a confident person smiling subtly" might generate a person smiling broadly or looking aggressive, because the underlying latent space struggles to disentangle those nuances. And the inference speed bottleneck for SDS, often requiring hundreds or thousands of steps, makes real-time applications challenging.
And for image-driven, it's classic data scarcity. You can have the best neural implicit representation method in the world, but if you don't have diverse, high-quality, ethically sourced 3D facial scans, your models won't generalize to the variety of human faces or expressions needed for realistic avatars. Think about custom avatar creation for gaming or virtual reality. This is a huge barrier.
It truly is. The cost of acquiring professional-grade 3D scan data, often involving specialized hardware and trained technicians, is prohibitive for many researchers and smaller studios. This creates a feedback loop. Limited data leads to less generalizable models, which in turn reduces the incentive for widespread adoption, further limiting data collection. Overcoming this will likely require entirely new data synthesis techniques or radically more data-efficient 3D learning paradigms.
So we have these critical, stubborn problems. But what about the underlying intellectual currents? Our report also highlighted some strong concept convergences like logogram and algogram with a weight of 10, and both converging strongly with curriculum engineering. This sounds like a drive towards more formalized, structured AI, particularly in educational contexts.
That's a very astute observation, Nova. The extreme convergence between logogram and algogram, both with 10 co-occurrences, signifies a powerful and sustained effort to formalize the very building blocks of AI reasoning. Logogram refers to logical structures and reasoning frameworks, while algogram points to the algorithmic design and procedural aspects. Their strong link suggests a recognition that robust AI needs both clear logic and well-defined, executable processes.
And then bringing curriculum engineering into that mix, also with a high weight of 9.0 and 9 co-occurrences with both logogram and algogram. This isn't just about general AI reasoning, it's pointing specifically to how we might build, teach, and maintain intelligent systems, particularly for learning and education.
Precisely. Curriculum engineering isn't just about human education anymore. It's increasingly about how we design, sequence, and optimize the learning pathways for AI models themselves, especially in continuous learning or adaptive systems. The convergence implies that researchers are applying formal logical structures and algorithmic principles, the logograms and algorograms, to create more robust, transparent, and auditable AI curricula. This addresses some of those recurring problems we discussed earlier, like the high demand for continuous updates and audits, or the complexity in aligning multiple standards, which are all related to educational or regulatory contexts. Exactly. It's about creating AI systems that can not only learn, but also articulate how they learn and why they make certain decisions, which is crucial for trust and compliance in sensitive domains. We also saw a significant convergence between Model Context Protocol (MCP) and Retrieval Augmented Generation (RAG) with a weight of 4.0.
That makes intuitive sense. RAG is all about augmenting LLMs with external knowledge, and a model context protocol sounds like a systematic way to manage and interact with that context, especially for agents.
It does. MCP likely refers to formalized methods for managing and updating the contextual information an LLM or agent operates within. When you pair that with RAG, which dynamically retrieves relevant information, you're talking about systems that can maintain a much more consistent, coherent, and up-to-date internal model of the world. This directly addresses the challenges we see with agentic LLMs failing validation by potentially providing more rigorous and traceable context management. It suggests an evolution beyond just raw retrieval to a more structured, protocol-driven approach for context.
So, despite the lack of brand new research papers, what we're seeing is a clear picture of the research community quietly but intensely focusing on hardening the core technologies we already have. They're trying to solve those fundamental, critical problems that emerge when you try to move from impressive demos to reliable, deployable AI.
That's the takeaway, Nova. This week's data paints a picture of a field hunkering down, tackling the gnarly, persistent problems rather than chasing the next shiny object. The focus on formalizing logic, algorithms, and context management indicates a push for greater rigor and robustness in AI systems, especially agents and educational applications. Okay, before we wrap up, let's take a quick look at this week's Industry Watch. It seems like the financial world certainly isn't quiet. Far from it, Nova. Q1 2026 saw a record $300 billion in venture investment, with an astounding 80%, that's $242 billion, directed to AI startups. OpenAI alone closed a substantial $122 billion venture round. This isn't just a surge, it's a colossal wave of funding, indicating immense investor confidence in the long-term potential of AI.
$122 billion for OpenAI is just mind-boggling. It underscores the commercial imperative to solve those hard research problems we just discussed. Investors are pouring money into a future built on these technologies.
Absolutely. That kind of capital infusion empowers companies to tackle those deeply persistent and resource-intensive problems, like overcoming the data scarcity in 3D generation, or developing robust frameworks for multi-agent systems. It's a clear signal that the industry believes the fundamental research challenges, though difficult, are solvable and immensely valuable.
And on the product side, Siemens unveiled its Eigen Engineering Agent. This is an industrial AI product designed to automate engineering tasks, moving beyond just guidance to autonomous functionality. That directly ties into the agentic AI discussion, doesn't it?
It does, Nova. Siemens entering this space with an Eigen engineering agent signifies a major shift towards autonomous AI in critical industrial settings. This kind of application will severely test the robustness, validation, and interpretability of LLM-based agents. If these agents are performing tasks in complex engineering environments, the recurring problems of false positives, context persistence, and authority boundaries become immediate, high-stakes operational challenges. It's a real-world testbed for the theoretical issues we just unpacked.
And we also saw OpenHand's 1.1.0, an AI-driven development framework, receive a significant update. It introduced a modular SDK, CLI, and a local GUI for real-time visual debugging. This is about making it easier to build and debug these complex AI agents, right?
Precisely. The Open Hands update is a practical step towards addressing the engineering gap in agentic AI. By providing a modular SDK and, crucially, a real-time visual debugger, it allows developers to peer into the agent's internal workings, its thought processes, its interactions with code and system commands. This direct visibility is essential for understanding why an agent might be generating false positives or failing validation, helping to identify and mitigate those critical issues we discussed. It's an infrastructure play to make agent development more transparent and reliable.
So, while the research publication pipeline might have been quiet, the industry is clearly pushing forward with aggressive investment and productization of AI, particularly in the agentic space. This creates an even stronger urgency for the foundational research to deliver robust, reliable solutions to those deep, recurring problems.
It's a fascinating dichotomy. The academic research community is in a deep, introspective phase, wrestling with fundamental issues of robustness, trust, and formalization. Meanwhile, the industry is scaling up, pouring resources into deploying these nascent technologies. The pressure is on for that foundational research to catch up and provide the bedrock for these ambitious industrial applications.
Absolutely. The next few months will be crucial to see if that quiet period in new papers translates into significant breakthroughs on these persistent problems, or if the industry's rapid deployment outpaces the underlying research.
That's it for this week's AI Research Weekly. A quiet week on the paper front, but one that highlighted the depth of the challenges we still face and the immense pressure from the industry to solve them.
Join us next time as we continue to track the cutting edge of AI, hopefully with some new breakthroughs to report. I'm Nova.
And I'm Onyx. Thanks for listening.